Today we will discuss a topic module from abstract algebra. So definition of module is: if R is a ring, a non-empty set M is called R module over R. If capital M is an abelian group under addition, and if small r belongs to capital R, then A belongs to capital M, such that RA belongs to M and satisfying three conditions. The first one is R A plus B is equal to RA plus RB. The second, R S A is equal to RS A. And the third one is R plus S bracket A is equal to RA plus SA, where R comma S belongs to capital R and A comma B belongs to M. Now there is another definition: if 1 belongs to R and if there exists small m belongs to capital M, such that 1 dot m is equal to m, then capital M is called uh, unital R module. Now there is a theorem: if R is a ring, lambda is a left idle of R, then the set of all cosets A plus lambda such that A belongs to R is module over R. Then this denoted by R by lambda or R minus lambda, and it is called the quotient module or difference module of R by lambda. R by lambda or R minus lambda is equal to A plus lambda such that A belongs to R. Now there is a proof. We've defined addition and multiplication: A plus lambda plus B plus lambda is equal to A plus B plus lambda. इसको इक्वेशन नंबर 1 नाम दिया. नाउ R A plus lambda bracket is equal to R A plus lambda plus lambda, equation number 2, where R belongs to capital R. Now we shall prove that addition is well defined. Let A plus lambda is equal to A dash plus lambda and B plus lambda is equal to B dash plus lambda, such that A dash comma B dash belongs to R. Now A plus lambda is equal to A dash plus lambda. A minus A dash plus lambda equal to A minus A dash plus lambda is equal to A dash minus A dash plus lambda, which is equal to 0 plus lambda. Why? Cancellation law. Now A minus A dash plus lambda is equal to lambda. So A minus A dash belongs to lambda. Lambda is a subgroup under addition. Similarly, B plus lambda is equal to B dash plus lambda. So B minus B dash belongs to lambda. Therefore, A minus A dash plus B minus B dash belongs to lambda, or A plus B minus bracket A dash plus B dash belongs to lambda, or A plus B minus bracket A dash plus B dash plus lambda is equal to lambda, since lambda is additive subgroup, or A plus B minus A dash plus B dash plus lambda is equal to A dash plus B dash plus lambda by cancellation law. Or it can be written as A plus B plus lambda is equal to A dash plus B dash plus lambda. A plus lambda plus B plus lambda is equal to A dash plus lambda plus B dash plus lambda. Addition is well defined. Now we shall prove that multiplication is well defined. If A plus lambda is equal to A dash plus lambda, then we shall prove that R A plus lambda is equal to R A dash plus lambda. Now A plus lambda is equal to A dash plus lambda, which implies A minus A dash belongs to lambda. So R A minus A dash belongs to lambda, which implies that R A minus R A dash belongs to lambda, which implies that R A minus R A dash plus lambda is equal to lambda, which implies that R A minus R A dash plus R A dash plus lambda is equal to R A dash plus lambda. So it can be written as R A plus lambda is equal to R A dash plus lambda. Now R bracket A plus lambda is equal to R A dash plus lambda. Hence the multiplication is well defined. Now we have to prove that R by lambda is an additive abelian group. Let A plus lambda comma B plus lambda comma C plus lambda belongs to R by lambda, such that A comma B comma C belongs to R. Now we will prove R by lambda is an एडिटिव अबेलियन ग्रुप, जिसके लिए पहली प्रॉपर्टी होगी क्लोजर प्रॉपर्टी। बाय फर्स्ट ए प्लस लैम्डा प्लस बी प्लस लैम्डा इज इक्वल टू ए प्लस बी प्लस लैम्डा belongs to R by lambda. Closure property is satisfied. Now another property is associative. So A plus lambda plus B plus lambda plus B plus lambda plus C plus lambda, which equal to A plus lambda plus B plus C plus lambda by first. So which is equal to A plus B plus C bracket plus lambda is equal to A plus B plus C plus lambda, which is equal to A plus lambda plus B plus lambda plus C plus lambda. This property is satisfied. Now the third property is identity. Since R is a ring, then 0 belongs to R, and so 0 plus lambda belongs to R by lambda. A plus lambda plus 0 plus lambda is equal to A plus 0 plus lambda by first property, which is equal to A plus lambda. So 0 plus lambda plus A plus lambda is equal to A plus lambda. A plus lambda is an additive identity of R by lambda. Now, by the inverse property, if A plus lambda belongs to R by lambda, where A belongs to R, which implies that minus A belongs to R, which implies that minus A plus lambda belongs to R by lambda. Now, minus A plus lambda plus A plus lambda is equal to minus A plus lambda is equal to 0 plus lambda. Similarly, A plus lambda minus A plus lambda, which is equal to 0 plus lambda. Hence, minus A plus lambda is additive inverse of A by lambda. Now, the fifth property is commutative. So, A plus lambda plus B plus lambda is equal to A plus B plus lambda by property 1. Now, B plus A plus lambda, since A comma B belongs to R, so B plus lambda plus A plus lambda by first property. Hence, commutative law is satisfied. If small r belongs to capital R, then R A plus lambda plus B plus lambda is equal to R A plus B plus lambda by first property. So, which is equal to R A plus B bracket plus lambda by second property. So, which is equal to A plus R A plus R B plus lambda by definition. So, which is equal to R A plus lambda plus R B plus lambda by first. R A plus lambda plus R B plus lambda by equation by second property. Now the third is if R small r and small s belongs to R, so R S A plus lambda is equal to R S A plus lambda by second. So which is equal to R S A plus lambda by second. R S A plus lambda by associative property. So R S A plus lambda by equation. Now the fourth one is if R comma S belongs to R, then R plus S and A plus lambda is equal to R plus S bracket A plus lambda. So R A plus S A plus lambda by definition. Now R A plus lambda plus S A plus lambda by first property. So R A plus lambda plus S A plus lambda by second property. Hence R by lambda is a module.